Have you ever really stopped to think about what happens when you flick on a light switch or plug in your phone? It all comes down to the magic of flowing electricity. So in this explainer, we're going to break down the absolute basics of electric current and make these everyday mysteries totally clear.
All right, so here's our game plan for today. We're going to start with a really simple puzzle about two lights. Then, we'll take a look at nature to understand the big idea of flow itself. After that, we'll meet the three main characters in our story: potential difference, current, and resistance. And to wrap it all up, we'll see how they all play together in the two most common types of circuits.
So let's kick things off with a little mystery. It's something you might see at a science fair, and it looks super simple on the surface, but the answer? Well, the answer unlocks the first big secret to understanding how electric current really works.
Okay, so just picture this, right? You've got two identical little LED lights. You hook up the first one, and bam! It gives this brilliant flash of light for just a second, and then it's gone. Dark. Then you connect the second one, and it just glows. A nice, steady, continuous light. So same lights, but completely different results. What's going on here?
Well, the secret, as you can probably see, is all in the power source. Over on the left, we're using something called a capacitor. You can think of it like a tiny water bucket that just dumps all its energy out in one giant, super fast splash. That's our flash. But on the right, we've got a good old-fashioned battery, which is more like a hose, providing a slow and steady stream of energy. And that's what keeps the light on.
So here's the big takeaway. The capacitor gives us a quick, momentary burst of electric charge, like that splash of water. The battery, though, gives us a continuous, steady flow, more like a river. And that continuous flow is exactly what we call electric current.
You know, to really get a handle on this idea of flow, let's just forget about electronics for a minute and look at the world around us. Because nature has some amazing examples that make this whole concept click. Think about water, right? Water only flows when there's a difference in height. It always moves from a higher place to a lower place. If the ground is totally flat, what happens? Exactly, nothing. No height difference, no flow. Simple as that.
And you know what? It's the exact same story with heat. If you heat up one end of a metal rod, that heat energy doesn't just stay put. It starts to travel from the hot end toward the cold end. The flow is all because of a difference in temperature.
And what about air? Imagine a tire that's pumped full of air. The pressure inside is way higher than the pressure outside. The moment you open the valve, whoosh! The air rushes out, flowing from that high-pressure area to the low-pressure area. Once again, it's all about the difference.
So you see the pattern, right? It doesn't matter if it's water, heat, or air. Things only move, they only flow when there is some kind of difference, a difference in height, in temperature, or in pressure. This one simple idea is the golden rule for understanding flow. Okay, so let's bring this idea back to our main topic, electricity. We can take that exact same rule and apply it here. For electric charges to start flowing, they also need their own special kind of difference.
Let's go back to our water example for a second. If you wanted that water to flow all day long, you couldn't just let it run downhill once. You'd need a pump, right? Something to keep lifting the water back up to the top to maintain that difference in height. Well, in an electric circuit, the battery is that pump.
Now, this electrical pressure has a fancy scientific name, potential difference. But you and I usually just call it voltage. And really, all it is the push that gets those electric charges moving around a circuit. We measure this electrical push in units called volts.
And we get that name from this guy, Alessandro Volta. He was the one who invented the very first electric battery, which was a huge deal because it was the first time anyone could create a steady, continuous electrical push. So it only makes sense that we name the unit of that push, the volt, in his honor.
So, just to be clear, voltage is the push, and electric current is the actual flow of charges that happens because of that push. We can actually measure how much charge is flowing past a point every second, and we call that unit the amp, or just amps for short.
Okay, so we've got a push, that's voltage, and that push creates a flow, that's current. But what happens when that flow hits an obstacle or a roadblock? Well, that's where our third and final key player comes into the picture.
So this German physicist, Georg Simon Ohm, figured out a really important relationship here. His famous law basically says that the more push, or voltage, you apply, the more flow, or current you're going to get. It's a really simple, direct relationship. More push equals more flow.
But Ohm also figured out that every material fights back against that flow a little bit differently.
This property, this kind of electrical friction that tries to slow the current down, is what we call resistance. And yeah, you guessed it, its unit is the ohm, named right after him.
This is a perfect way to picture it. You can imagine the voltage as the force pushing from behind, the current is the little guy trying to get through the wire, and the resistance is this big squeeze in the middle, making it super hard to pass. The bigger that squeeze, the higher the resistance, the harder it is for the current to flow.
All right, we've met our three main characters: voltage, current, and resistance. Now for the final piece of the puzzle, let's look at the two basic ways we can wire everything together in a circuit.
So on the left, you've got a series circuit. The easiest way to think of this is like a single-lane country road. The current has only one path it can take, so it has to go through every single component one after the other. But on the right, we have a parallel circuit. This is more like a big highway with multiple lanes. The current gets to a split in the road and divides up, with some of it going down each separate path.
And this table really shows just how different these two setups are. So let's just walk through it. First up, the series circuit. Because there's only one path, the current is exactly the same everywhere. But the voltage, the push, gets divided up and shared between all the components. And here's the biggest problem with series circuits. If one of those bulbs burns out, the whole road is blocked. The circuit is broken, and everything goes dark. Now let's flip over to the parallel circuit. This is where it gets really cool. Here, the voltage is the same across every single branch. It's the current that gets divided. And check this out. If one bulb fails, the other ones don't care. They just stay lit because their path is still complete. And here's the really mind-bending part. The more paths you add, the easier it is for the total current to flow. The total resistance actually goes down.
And this isn't just some abstract idea from a textbook. This stuff is used in pretty much every gadget you own. The way batteries are put into your TV remote versus how they're arranged in a power bank is a very specific design choice. It all depends on what that device needs to do.
So let's end with a little thought experiment to tie it all together. A TV remote needs a bigger push, more voltage to send its signal. A power bank, on the other hand, needs to supply a steady current for a long time. So, based on everything we just talked about, which one do you think uses a series connection and which one uses parallel? The answer is hiding right there in the rules we just learned.